We're beginning our discussion right now, and we're gonna solve a wide range of questions. Right, so today we begin by looking at how we can attempt to solve the differential equation below. I gave you this question, but we have a chance to do it today. I gave you this as an exercise, okay, sometime back. Right, below, by means of the Taylor series expansion, so just recapping on the Taylor, but obviously we're looking at the second order differential equation. To get the value of y evaluated at 1.1, use terms up to x6, and the change in x or age is 0.1. Right, so we are good with this. Right, so we look at what we said for the Taylor method. Right, so in an attempt to approximate the Taylor, this is how we do it. I gave a formula last time, and I'm going to recap on the formula. Right, so we said that the Taylor series can be determined by actually expressing a function f is a sum of the values of the function. So that would be the value of the function evaluated at a, for example. And then we add f primed at a into x minus a, and we divide by 1 factorial. Then we can have the second one, x minus a, you square that over 2 factorial. Okay, we can express this in sigma notation, and therefore we have the third derivative of the function evaluated at a, and then we have x minus a, you cube it. You divide by 3 factorial. Okay, this is the pattern. You can just write one more, etc. The fourth derivative, a variant notation, and you have x minus a, you divide by 4 factorial, and this goes on and on. We understand that this must be up to x to the power 6, so obviously this will be x to the power 4. And then now it goes up to infinity. So in other words, this idea of the Taylor series can be seen in view of this formula that we're going to use for a function f. So this is a very powerful result just to mention, because this Taylor series is celebrated much because it actually has implications. It means that we can express a lot of functions as Taylor series, and this is a very powerful result. In other words, we can express the log as a series, the log function. We can express the exponential function as a series, and this here is a very, very powerful, but extremely powerful result. So we take note, but I will make mention of the fact that at this point, you can go on here, and the general term becomes good to write so that one can see how we generalize the whole thing, so that you have the nth derivative and then x minus a to the power n, the nth derivative, obviously put in brackets, and you divide by n factorial. Okay, so this is exactly the notation. Now, how to use this formula to solve this differential equation? And in particular, this here is an initial value problem with two initial values, namely y at 1 is 1, and also y primed at 1 is the integer 2. Now, this is how we do it. Right, this is how we do it. So we proceed as follows. Right, so we do the relevant substitution. So first things first, we need to note is that now to answer the question, to find the Taylor series of the function at x equal to 1.1, first things first, we need to first evaluate the um the derivatives. So there are consecutive derivatives we need to actually evaluate. Okay, right. So the consecutive derivatives we need to evaluate actually evaluated at um a series of these values, and we shall determine that. But first things first, I will say we observe that um this expression we've written here, it is necessary to say we shall approximate. We shall approximate y. Y is just the same as f of x. So we shall approximate y um, at 1.1 by the truncated power series. Okay, by the truncated Taylor series, which is the Taylor series has properties of what we call power series, which is a more general notion of what we call series. Okay, right. So now we then say now we shall therefore write 1.1 as they wanted. And this 1.1 then is the same as, So it becomes the same as the following. So you make the observation that the number 1.1 and h is 0.1. So it means therefore you have 1.1 is equal to 1 plus 0.1. So it means the change is just 0.1. Right, and if the change is 0.1, it actually means that A is equal to 1 in this formula. Right, it means A is equal to 1. And if A is equal to 1, it means therefore our H itself is 0.1. Right, so and that means therefore our right, it means therefore our A is 1, but I want to mention something else. Right, so obviously, okay, look at this. If our A is 1, here in any of the terms, maybe this one here, we shall have, because I want to say this, okay, let me say explicitly, and then we shall make a draw a one-to-one correspondence. So the 1.1 can be approximated as y at 1 plus 0.1 into y primed at 1, and then you have so in other words, this formula I've just written can be written like this. Right, so you have 0.1, and then you square this one. You divide by 2, and then you have y double primed at 1. So I want you to draw the correspondence with this. And then you have 0.1. You can raise it to the 6th power because it's up to x to the power 6. And then you divide by 6 factorial, and then it is y to the power, well, the 6th derivative. You can write 6 like that in parentheses, and then this is evaluated at 1. Okay, we're able to observe this here, and the fact that we can see that A is 1, and therefore it means therefore the difference between x and A. So x minus A, what is this difference here? So the difference between x and A, so in other words, x here we are dealing with is 1.1. So, and then A itself is 1. So, okay, we're looking at this here. This is very, very, a very important result. Right, so we have this. Okay, so Okay, so at this point, what do we do? Right. Okay, I'm just want to make sure this X is very clear. Okay, so now we have this. So we have X minus A. And then it's exactly 0.1. Okay, so this is good because now it shows us what we are doing. Because X in the question is, if X is given to be 1.1, with the I've written this as a Taylor series that is done at first year or second year, and also in the real analysis modules. Right. So you realize therefore that X is given here, and that means that now and the change X is given, and that means what you do is you realize that okay, becomes X minus delta X, or which is the same as X minus A in the notation I used here. 1.1 minus 0.1, and therefore this is what 1. So right, so it becomes right, let me see what I did here. Right, so it becomes X, which is 1.1, yes, minus 0.1, which is 1. Right, but also I want to mention that X minus A, right, X minus A, X minus A, this one here, which is X is 1.1 in the question, A is 1, and therefore the result is 0.1. Why am I mentioning this? Why is X minus A mentioned? Because it appears in the formula. So wherever there is X minus A, you put the difference 0.1. Okay, try to understand this. Now, what then we are effectively saying here, what we do with all these things here, right? We are better placed now to begin solving the problem. So we do the derivatives at x equal to 1 are calculated in the way illustrated there. So in other words, we compute the derivatives. Now, this is very important. So we shall compute. We shall compute the derivatives at what value of x? So we shall compute derivative at x equal to 1 as follows. Okay, so yeah, this derivative shall be computed at x equals to 1. Okay, you know that. So let's start now computing the derivatives. So we know that from the given question, that what we have merely is the second derivative. So the second derivative of the function is given as xy squared minus 2y primed plus x cubed plus 4. Right, so, okay. Now we have the derivative. Well, it's exactly nothing new here. What have we done here? This is exactly the given differential equation. Okay, so, but now we need to compute this. So this means we can find the second derivative. You can evaluate it at 1. And now evaluating it at 1, we shall have 1 for x. And then what is y? It is 1. So in other words, from the initial condition, x is 1 and y is 1. So we shall have that x is 1 and then y is 1 squared. Okay, minus 2 into y. 1 from the initial condition here above. And then we have y primed. What is y primed? Y primed at 1 is exactly what? Is exactly 2. Okay, and then plus the x cubed. What is x? X is 1. Okay, and then we add 4 to this. Okay, this is just basic algebra, and the result is 2 then. Okay. The next thing is we shall do the other derivative. So the other derivative is computed as follows. So the other derivative is computed as follows. So we shall do the third derivative of the function y at x. Right, so here, this one, we're going to use the product rule of differentiation because we have a product of x and y squared, for example. The derivative of the x is 1, giving us y squared. The derivative of the x is, we keep the x constant, we differentiate y, and therefore it becomes 2x y. Okay, because the derivative of the y squared with respect to x becomes 2y. But not just 2y, and then we put y primed. Okay, by a method we call implicit differentiation. So we have minus 2. The derivative of the y is the first y in the product here of 2y, y primed. Of the first y, if you differentiate the first y, you get y primed. But there's another y primed giving us y primed squared. All right, and then we continue. We add, but there is a minus 2 there, so we're going to maintain the minus 2 number. And then we find the derivative of y primed. What is the derivative of y primed? Is y double primed. Right, and then the derivative of the x cubed is 3x squared. The derivative of the number 4 is 0 because the number 4 is a constant. And the derivative of a constant is clearly what? Is clearly 0. So this one here is evaluated at 1. Okay, you need to understand why the derivatives of these derivatives, which are continuous derivatives, consistently evaluated at 1. So now this one here, let's see what we get. Okay, so this one we do substitution. What is y? Is 1 from the initial condition or initial conditions, which are 2 of them. All right, we have 2. X is 1. Okay, we're evaluating is y triple prime at 1. So we have a y. What is y? A y at 1 is
Hello?
1. Yes, please. Y.
Can you explain the derivatives again? I'm confused.
These derivatives in the third derivative.
Yes.
Okay, that's fine. Right, so let's just discuss the derivatives. So I'm just going to recap on that one a little bit now. All right, I'm just going to recap on that. Right, so these derivatives themselves are very important. Right, I'll just elaborate a little bit on that. Okay, in view of the implicit differentiation. Implicit differentiation is the form of differentiation we use when we have several variables, and y is not the subject of the equation. Quite. Okay, that is what we normally use when we have multiple variables there. Okay, so let's use this now. So we're gonna differentiate now here. If I differentiate here first, we differentiate from the y double prime. The derivative of x is 1. So we have differentiated x with respect to x, and we got 1. The product rule says you must add. Right. The next thing is you keep x constant, and then now you must differentiate y squared. But y squared with respect to x is a function of y. So it's going to be 2y. But because the function is a function of a different variable. Okay, I want to mention this here. I want to mention this like here. Okay, let me explain somewhere here. Right, so if you are to look at what happens here in just a second, right, in just a sec. Okay, okay, I'm here. Right, so I was just wanted to say, if you are to find the derivative of the x of y squared, let's just find y squared, something easy. Right, so you have, with respect to x, obviously we find the derivative, so you have to find the dy, and then you put y squared, and then you do dy dx. Right, so the derivative, therefore, of, so you do it like this in detail. the derivative of the y squared. Now, with respect to y, we have introduced the dy, but the dy cancels out. And then you'd have 2y, and you have dy dx. So obviously, we agree, therefore, that the dy dx, we use the prime notation, so that is going to be primed there. So which means when we get here now, we're going to use exactly that method of we're using the method of the prime because it is very convenient for us. Okay, right, so I'm going to use it straight away here. So now, at the bottom of the page, of the slide, so what I'm going to do is we differentiated first x and we got 1. And then y squared was kept constant. And then now we keep x constant, we differentiate y squared. Right, y squared derivative is 2y. And then now we shall have the y primed, okay, which is coming from the above explanation there. Right, so now we have -2. I can keep the -2 out. And I focus on the product of the functions because that is where the differentiation happens. And now we're going to differentiate the y first. The first y, the -2 is the constant, so you can leave it out. If we differentiate y, the first y is going to be y primed, and then we keep y prime constant. And the product rule says you must add. So we put the addition sign, and then we have the derivative of the y primed, which becomes y double primed. And then we have so we're done with the -2y primed, and we have x cubed. The derivative of the x cubed is the same as y with respect to x. It becomes 3x squared. The derivative of 4 is 0. Okay, so we're going to do substitution. The third derivative of y evaluated at 1. Okay, so we evaluated at 1. One hint that we evaluate this at 1 is because of the initial values we're given. Y at 1 in the problem itself. Y at 1 is 1 and y primed at 1 is 2. And meaning we evaluate them at 1, we understand that we need to evaluate the derivative, the series of the function at 1.1. So that is very important to sort of make sure one understands that because there's a pitfall there and there's a possible chance of confusion. All right, so y squared will be 1 squared. And then we have a plus. What is x? Right, what is x? X is 1, right? Because we evaluate this at 1. So it's y of x, so y of 1. Right, so we have here 2. What is y at 1 is 1. Y double prime, y first primed. Y first primed is 2 in the problem, initial value. Right, so we have this one. Right, we subtract 2 into, what is y primed at 1? It's 2. So we put 2 and then we multiply by 2. Plus y is what? Y is 1, and what is y double primed? We got y double primed from above, so this builds up on the previous. Right, so y double primed is 2 from the previous one, and then we put 3. Right, and then we have the following. Right. Right, so you continue. We continue. So what is 1? Okay, so we continue. All right, so the x is 1, so you put a square. Okay, we just need to simplify this one. Right, so just basic algebraic manipulation. So the third derivative at 1 becomes a -4. You can always check that, but it works out to a -4 if you add all these numbers here. Okay, right, so we continue. Right. Right, so we continue now. Okay, we found the third derivative, but remember that we must do 6 of them because we must do up to x to the power 6. So we're going to do 6 derivatives. Right, we're going to do the 6 derivatives because we must go up to x to the power 6, up to x to the power 6. Okay, so we're going to do 6 derivatives. Okay, let's do the fourth now, the fourth derivative. What is the fourth derivative? So I'm going to do it on the next slide. Right, so the fourth derivative is as follows. Right, so we first, for us to do the fourth derivative, we must write the third derivative. So what is the third derivative? Right, we remember the third derivative is from the previous one, so I'm just going to write it down. So the third derivative, which we found just above. So it's y squared, and then we add plus 2x y, and then we have y squared. That's the third derivative minus 2y primed squared. You can write it like that. Minus 2y, y double primed, and then plus um um there are all sorts of typos sometimes in these things. Right, so let's just look at this very, very carefully. Right, so what I'm going to do is to avoid mistakes here. I'm going to write the second derivative first, and then we're going to work it out ourselves. Okay, because sometimes these guys make mistakes, in these things we use. Okay, so I'm going to just write the okay, so right, I want to remove this. First, I want to write the second one because sometimes they make typos here. Right, so I want to rely on what we can understand and what we can test, experiment and obtain ourselves. Okay, we remember that the second derivative was given in the question, so that one will be right. Right, so which is y double prime of x, which is x, y, and so on. Yeah, I'm gonna waste a little bit of time here. Let me just use our third derivative. Okay, because we're using the third derivative from obviously our resource pack. Need to, I'm using a different slide. So if I move to the next slide, I cannot see the previous, but it's okay. Now I've just taken a screenshot on my side of the previous thing we got. Right, so we'll remember a couple of things that at this point, what we have. Right, so we have the third derivative we got ourselves. Okay, just one sec. I'm writing it down. Okay, I want to write the correct thing because I can see that there's already a mistake in the thing, in the material that we use. So now it means here, we shall have the third derivative we got ourselves. Okay, we use the product rule and it's correct. Right, you can always double check that. So it's okay. So we have 1 y squared. And then plus x 2y primed minus 2 into y primed, y double primed. And therefore, this is plus 3x squared. Okay, from this, we're able to, yes, please.
Can you see the annotations on my screen?
Yes, I can see. Right,
Okay.
okay, 1 minute. They're gone now. Are they gone? Yes.
I still don't understand the derivatives.
Okay. All right. Are you able to see my screen clearly now?
Yes.
Okay, because there was an annotation for a couple of seconds, and then it went, right? So the screen is clear now. Okay, because suddenly something was landed on the screen. It's just technology. Mhm.
Yes, I put that.
Okay, thank you. Oh, okay, because you don't understand the derivatives. Okay, thank you. All right, thank you. Right, so that's okay, I understand. Okay, so let's do the derivatives now. Okay, because you don't understand the derivatives. All right, let's just um right. So let's do. Okay, let me see what we can have here. Okay, obviously here one thing you can look at is, are there any like terms in the derivative before you do the next one, to just avoid lots of expansions and long things. So let's do the next derivative. Doesn't matter. Right, we can do the next. We can do the next one. What is the next one? Right. So the next derivative is going to be y, the fourth one. Okay, you'll get familiar with it as you go. Okay, let's look at the fourth one. Okay, there's a 1 there. That 1 is just a number, so we just have to differentiate y squared with respect to x. So it becomes 2y. But because it's a function of y, we multiply it by the derivative of the variable. Okay, it's just the implicit differentiation, this and the chain rule of differentiation. Okay, so we continue. And then now we continue. And then we find the derivative of x. What is the derivative of x? Okay, this one is a bit tricky because it has 3 terms. So you have 3 terms that are multiplied together. But it's easier. It's not a huge deal. The derivative of x is 1. Plus x. What is the derivative of the 2y primed? Okay, you can just keep the 2 out if you want, but you can just, the derivative of the 2y primed, first you differentiate the y, and then you get y primed. Next, the 2 is a constant way number, so we don't worry about it. And then here you differentiate the y primed, becomes the second what? It becomes the second derivative. Okay. So we get this one. Okay, you're gonna be a bit faster because I know that this is not it's something we need to, because this question is there in the exam, very, very likely. The chance of this question being in the exam is like 98% of the, it has that probability of appearing, so it has a very, very high chance of appearing in the November, October exam. I need to just take the exam date for this one, October, November. Right, so let's do the derivative of, okay, now we should have just expanded this one and wrote it as y primed y primed times y primed. Okay, so yeah, we can find derivative. Okay, the derivative of the first one, y primed, is going to be y double primed. And then we have y primed. The derivative of the second y primed is the double primed. Okay, so this one is the product of 2 terms, and therefore we use the product rule of differentiation. All right, we find the derivative of the y times y double primed, so we do y prime. Right, and then we put y double primed. And then we keep y constant, the derivative of y double primed, because it becomes triple primed. Okay, and then the derivative of the next one, 3x squared, becomes 6x. All right, so without adding things up, we can add things up, but we might just be equally wasting a lot of time there. So which means you can find a fourth derivative, and we just substitute from the initial values. We know very well that y at 1 is 1, and then y primed at 1 is 2 from the initial values. And then we have here 2, y at 1 is 1, y primed is 2 from the initial values. Okay, so we continue. Okay, so the x is x at 1. Y, we're evaluating everything at y at y at 1. We're finding y primed at 1, y double primed at 1. So x is 1 in this case. Okay, and then we have 2. What is the y primed? At 1 is 1. Is 1. This one at 1 is 1. Double primed? We got it. Right, so we got the double primed. We got double primed to be 2. Okay, we got the double primed to be 2. Okay, so, but yeah, it's very interesting that one just looks at carefully and checks if this is not a mistake here. No, it's not a mistake.
Hello?
Yes, please. Yes, please. Can you hear me?
Yeah, yes, I'm still confused at this
Yes.
part.
The derivatives,
This
huh?
Yes, I
Oh,
don't know how you do
that
that.
part. You don't quite understand that part, right?
Oh, still.
Okay, that's fine. Okay, let me recap on that. Let me recap on it. Okay, let me recap on it because I'm interested in us getting the correct answers here. Because sometimes it's very important to make sure that. Okay, Okay, to make sure and I explain well, I'm gonna just do what? I'm gonna just erase, and it's not a lot to write. It's not a lot to write. So I'm going to write it again and try to use a different, a slightly more, perhaps clearer way of writing and explanation. Okay, let's look at these because the exam is here. You sent me the exam timetable. Okay, so we continue. Right, so now let's look at this now. Okay. Okay, let's look at the bottom thing. Thank you. You put that in patience there. Right. So let's look at the third derivative here of this. Okay, because the second one was given. What is the third derivative? So we differentiate this one one more time. So getting higher order derivatives. And first we look at the products and quotients and sums. Right. So we first find the derivative of x. What is the derivative of x? Is 1. Right. We keep y squared constant. And then the product rule says if you have a product, you must add. Right, so we keep x constant now, and you find the derivative of y squared. What's the derivative of y squared? Okay, so this one we use the chain rule. Easy to use the chain rule straight away. So if you use the chain rule, what does the chain rule is used when we have powers of functions and higher powers of functions, and you want to find the derivative of that. And the chain rule says if you differentiate y squared, you'll have to bring down the power. And then now you multiply by the derivative of what is under the power. The power is 2 on the y, you have y squared. So what is under the power is y, and then we multiply by the derivative of what is under the power. It is y, so we find y primed. Okay. Now, the next thing is we have minus 2y primed. So at this point, y primed is what? You find the derivative of the y first. The minus 2 is a constant, so we keep it out of this. Put some brackets outside. Okay, now the product rule is going to work on the inside. Y times y primed. The derivative of the y is what? Is the first y is y primed.
Hello.
Yes, please.
I think there's rules I don't know because I don't understand where this
The
this
primes are
part
coming
came.
from.
I don't
Oh, we
understand
don't
this.
understand where that part is coming from. I understand. Okay, okay, that's fine. Let me speak about the rules a little bit. Okay, thank you for mentioning that. Let me speak about the rules. Okay, I'm going to mention the rules on the other slide. Okay, so I'm going to do this on the other slide. Okay, so I'm going to do this on the other slide. So first, I'm going to state the product rule. Okay, because it's what we're using here. And also, I'm going to state the chain rule. Okay, so let me just remove this. I just remove this here. Because the Taylor is part of what is very important, but also is very important in mathematics because it is what does Taylor series generally, the Taylor series, what does it do in general in mathematics? It helps us to express any function that is mostly continuous as a series. So a function we can express sine x as a series and so on. And this is a very powerful result. Okay, now let's do this. Right, so we continue. Right, so to do this now, I'm going to first write down the question. Okay, not really the question, but the second order derivative which was given. So the examiner gave us the squared y, and then they gave us dy squared. Okay. And then now I'm just recapping on that one. Don't worry, because it is part of the thing. All right. We have it on the next previous page. Yeah. So it is xy squared minus 2y primed plus x cubed plus 4. So now let's look at this. I'm going to just go horizontally. So now this is y. We can write it like y double primed of x is the same as x y squared minus 2y y primed plus x cubed plus 4. So what do we do here? We find one more derivative, but first I'm gonna state something we call the next rule. Right, so the next rule that we're gonna use is called the Um, the product rule. Right, the product rule of differentiation. Okay, there are many product rules, but here our focus is on the product rule of a differentiation. What does the product rule of differentiation state? Right, so it states that um, we can find the derivative of a product of functions. So y is a product. We can let y be a product of two functions. Then now the product rule explains to us that we can be able to find the derivative of the product. So it is over, it's dy dx, dy dx. So we can find dy dx like this. Okay, so first we find f primed. Derivative of the f is f primed. What is the derivative of the g is g primed. So this is the rule. It's called the product rule of differentiation. And then next I'm going to state something called the chain rule. Right. What does the chain rule say? The chain rule. Right. So the chain rule says that if you have a function y, so there are many ways, so smarter ways in mathematics you can state it. So you can let y be a function of another function. So a function that is inside, no matter you state it like this. Right. We have a function inside another function. And now this involves powers of functions and arguments, etc. Right, so we're going to discuss those and look at examples. So dy dx. So how do we find the derivative of this one? It is f primed of g of x, and then you multiply it by the derivative of the g. Okay, this is the chain rule. Now, with this said, we just use basically these two rules. Let's find the derivative of the question at our disposal. Right. So what is the derivative of the function at our disposal? So now we want to find a third derivative. So we're going to move from the original, this one here, given the question, to a new one. So we're going to find now y triple primed, right, of x. Right. So obviously we have this. Let's find first. Now we have a product, so we're going to use the product rule. The product rule says you differentiate the first one because here we have the first function is f and the second is g in the product of the functions f and g. So we're going to use that. So the derivative here of this xy squared, the derivative of the x is 1. And then we have y squared. What does the product rule say? You put a plus. And then f was differentiated, and then now f is kept constant. X was differentiated, we got derivative 1, which is kept constant. The derivative of the y squared is what? The derivative of the y squared is 2y. Right, into the derivative of the y is y prime. So we are using the chain rule to differentiate y squared because it's a power. You differentiate the power. So now to differentiate y squared, we first differentiate y squared. Derivative of y squared is 2y. Bring down the power, then subtract 1 from the 2, and you get 2y. But the chain rule says you must multiply by the derivative of what is inside. The derivative of what is inside is uh, the inside function is g. So multiply by that one. So here the function under or inside, because if it is y squared, you can look at it as y squared like this. So the exterior function is f, but the interior function here is like g, which is equal to y. G of something is equal to y. Okay, whatever the thing. Yeah. Okay, just to note that and make sure you sort of understand this. Right. Make sure you understand that. Now, let's continue. Let's see. Right, so let's move on. Um, so you have minus 2 now. We have another product of the two things. Y primed. Okay, we find the derivative of y. Derivative of y is y primed. Then we have y primed plus. Then we have y. What is the derivative of y primed? Is y double primed. Okay. The derivative of the x cubed is what? Is 3x squared. Okay, the derivative of the 4 is 0. All right. So let's continue. All right, without wasting much time, we have these. We have this. But this we can add the things up. So you have this one, which is you can write it as y squared, and you can write it as plus 2x y primed minus 2y primed, and then you square everything minus 2y double primed plus 3x squared. All right. Now it remains to just do the substitution. Y triple prime to evaluate this as 1. So y at 1 is 1. Initial values from the previous page to x. X, everything is y at 1, so we're evaluating x as 1 already. Y at 1 is equal to 1 initial values. Y primed at 1 is equal to 2 from the previous page. Minus 2, and then now you have y1, y primed at 1. Okay, it is 2 from the initial values of the question, minus 2 y at 1 is equal to 1, y double primed. Y double primed. We got that one from the previous, and we just checked that one is 2, no mistake there. Okay, no mistake in the arithmetic. Okay, how far are we? How far are we? Okay, it's minus 2 that. Then plus 3. X is 1. And then you square that. Right, so which means it is y triple primed at 1. So you have 1 plus 4, 5. 2 by 4 is 8. Right, so we have 5 minus 8 minus 3. Getting minus 3 minus 4 is minus 7. Plus 3 is minus 4. Okay. So this is correct. Okay, we got minus 4 for the third one. The derivative, and then now we continue to the fourth. Okay, we need 6 of them. Okay, so we need a marathon a little bit, but this pattern repeats. This pattern repeats. So you have y for the derivative. Okay. Now sometimes when it comes to the fourth derivative, we just put a 4 in brackets. It's convenient that way than to put so many primes. We can have the difficulty counting the primes. So we can just put the fourth derivative at x. Fourth derivative at x. Okay, let's find the fourth derivative of this guy, of that equation. Right, so first we have y squared. What's the derivative of y squared? With respect to y squared becomes 2y. But because y is not x, we to find derivative of the y itself. So multiply with derivative of the y, because it's the chain rule. You differentiate first the exterior function and then multiply with derivative of the interior function. Right, so now we have 2. The derivative of the x is 1. So first we will find derivative of x. Hey, the product rule says you differentiate term by term and you add. So first we've done derivative of x. Derivative of y now, so we keep x constant. The derivative of y is just going to be y primed. Okay, we keep y primed constant. Plus 2x, and then we have y. The derivative of this one is the derivative of the y is y double primed. Minus 2. Now we have the derivative of the y primed. Right. So y primed squared. the derivative of that one by the chain rule. The chain rule says you must bring down the power. So we bring down the power. If it is a numerical value, then we subtract 2 minus 1 is 1 power 1. And then the derivative of the y primed is now the second derivative. Okay, so we're done with the derivative of this one. And then now we find to y. The derivative of the y is y primed. And then we have, we keep this one constant. The product rule says you must add, but there's a -2 there, so it's going to change the addition to the -2. Okay, and then we have y. The derivative of the y double primed is going to be what? Y double primed is going to be the third derivative. The derivative of the 3x squared is going to be 6x. Okay, so this one is the fourth derivative. White one. Now let's look at this one here. So you continue to substitute. Okay, we can just substitute straight away. We can, but it's easier to add the things a little bit. Okay, I then like terms. Okay, because now we need the fifth derivative and then the sixth. Okay, right. So y primed, do we have y primed? Yes, there are lots of them. There's a y primed in the beginning. The second one is y primed with the coefficient 2. And there's just a y primed. Let's see. It's only 2 of them, and then they give us 4. Right. So we have 4 y primed. Okay, we're trying to add the terms up to avoid lots of long expressions here. 2xy double primed. Well, 2xy primed times y primed. 2xy primed times y primed is only 1, okay, in the equation. So we can keep this one. Okay, to make it easier for us to do the next derivative. Okay, right, so, okay, what about 2xy double primed? 2x, y double primed. Now we have -4. Right. So we have y double yeah, y primed, y double primed. Anything like that? Y primed, y double primed is the only one? No, there are 2 of them. What have I done here? Okay, the y double primed has 2, and then there is another one 2, so it's gonna be 6. Right, so it's gonna be 6. Okay, let me just okay, this thing's already been done, so I'm just cross-checking, obviously just to make sure that the arithmetic is correct. So it's gonna be 6, this one. It's gonna be 6. So let me just do this. Okay, I was saying the 2x y double primed is only 1. Okay, but the y double primed with a number in front, constant in front, there are 2 of them, but the 2 by 2 is 4 in the -6. -6 y primed, y double primed. So we're done with those. Okay, what about y triple primed is only 1. So let's do that one. Y triple primed plus 6x. So you have, okay, here, please, it is still, yeah, it is still, what? It's still x, so it's y primed at x. Right, so, all right. Okay, let me look at this one. So you have 4, evaluated at 1. All right. Okay, let's do this quickly. Right, so what is y1 is 1. Y primed at 1 is 2 plus 2. X is 1. Y primed at 1 is 2. Initial values is 2, but you square it. X at 1, Y at 1 is 1. Y double primed, we got that one. Right, Y double primed, we got it to be 2. So substitute here 2. Minus 6. Y first primed, initial value is this one is 2. And then this one is what? Y double primed, we already got Y double primed, right? We got Y double primed to be 2. Hey, you square, no, there's no square, right? So minus 2. Y at 1 is 1, initial values. Y at the triple prime, we got it to be minus 4 plus 6. X is 1. Okay, we must just add everything here now. 4 by 2 is 8. Right, and then this one is 2 by 4, which is also 8. 8 plus 8 is 16. 16 plus 4 is 20. 20 minus 24 is 4. Minus 4. Minus 4. Minus 4 plus 8 is exactly 4. Plus 6, 10. Yes, okay. So this one is 10. So which means the fourth derivative is 10. Right, so the next thing we're going to do right now is the fifth derivative. Okay, so let me just move to the next slide. Then we're going to just do the fifth derivative. Right. Right, so on the next slide right now, we have the fifth derivative. What is the fifth derivative? Okay, to do the fifth derivative, we need to remember the fourth one. Right, so the fourth one is as follows. And why that is, okay, just one sec. This was not written clearly. Right, we must remember that's the fourth derivative. The fourth derivative. Right, so let's do the fourth derivative. What is the fourth derivative? Right, so you have the fourth derivative because the fourth derivative, you put it in parentheses, equals. We are trying to remember it from the previous slide, but also it will help us to find the next one. We added all the terms up, and what we got was, we got 4, then we got y primed, plus 2x. And then we got y primed squared. Two x y double primed. Minus 6 y primed, y double primed. Goodness me. Minus 6y primed, y double. Minus 2 y triple primed. Plus 6x. Okay, this is the fourth one. The fourth derivative from the previous slide. So we're gonna use this one to do the fifth one. So the fifth derivative. Okay, 4. Okay, now we differentiate first y, and then it becomes y primed. We keep y primed constant. And then we have for y, we differentiate y primed, we get double primed plus 2. The derivative of the x is 1. We keep y primed squared constant plus 2x. By the chain rule, now we have a power to differentiate, use the chain rule. So the chain rule says you differentiate, you bring down the power, and that's what we're doing. Subtract 1 from the power, but if we subtract 1 from 2 is 1, then the chain rule says multiply by the derivative of the interior function. And the interior function is already y primed, so the derivative is going to be the second prime. The derivative of this one. Okay. Right, so let's see what we're getting here. Okay, that's what we got. Then next we have 2xy double primed. 2xy double primed, so derivative of the x is 1. Y double primed, we keep that one constant. And then we have twice x. The derivative of y double primed, we differentiate y double primed, it becomes y triple primed. And then we have, okay, where's in the product rule, each time we see product of functions, the minus 6y double primed is minus 6y. The first one we put the double primed. And then the double primed is kept constant. But there's a minus 6 we must add. But the minus 6 changes the plus just to minus 6. So we have y primed, and then we find the derivative of the y double primed. It becomes what? The derivative of the y double primed, it becomes triple primed. Minus 2. The derivative of the y is y primed, the first y. And then we have y triple primed. Minus 2y, the derivative of the triple primed becomes, okay. The triple prime becomes fourth derivative. So I can just, instead of writing too many primes, I can just put it in parentheses, because now then the whole thing becomes untidy. So is the fourth derivative thing. Right, so now the derivative of the 6x is 6. So y at 1. Right, so we do substitution, we can add things up. Okay, any like terms here? Okay, the first term is y primed, y primed. Is there any y primed, y primed? Y primed, y primed? Right. Let me just substitute here. Okay, so y primed we know is 1, initial values. Y is 1. No, y primed is 2. Is okay, initial values in the original question. Okay, what I mean is this one. Y primed is 2 and y at 1 is 1. Okay, just remember that to avoid mistakes here. Now I'm gonna clean this up. Need to write the correct things here. So I will. Okay, so we're 4. Right, initial values and the previous values we got. Right, so we know that y primed is 2. Okay, y primed is 2 plus 4. Y at 1, initial values is 1. Y double primed is 2. Y primed, right, okay. Y primed is 2, x is 1. 2. Y1 is what? Let me see. Okay, y primed is 2. Y double primed is also 2. And then 2, 1. Y double primed is what? Is 2. Okay, we did that previously. Yx is 1. Y triple primed is -4. -6 into. Okay, y double primed is 2. Okay, so but you put it twice. All right, y primed is 2. Y triple primed is -4, -2. What is y primed? 2. Y triple primed -4. What is y? At 1 is 1. Okay, right, so continue. Continue. All right, this is basically the last one. -2y, not quite the last. Okay, -2y, and then y to the fourth. What is the fourth derivative? What did you get the fourth one to be? Okay, wait, we got it to be 10. Right, we've already the fourth one and it was 10, so we're gonna just put it here. Last 6, the last 6. Okay, these things are just like a chain of things. Okay, it's popular in applied mathematics to have these kinds of equations and two-man derivatives. Is what characterizes this. You write lots of derivatives, but normally this is easier. This is like mathematical literacy for university research. So we regard this as basic because we say just know one rule and just keep repeating the application. Okay, let's add everything here. Add everything here. I know that it's a task, but if you add everything here, the result is 78. Okay, you can always check that. Let's move on to the sixth derivative. So the sixth derivative, so we're gonna differentiate the fifth one. Let me use a different color, otherwise we are just gonna be bored by the same color here and we're gonna lose concentration. Everything is gonna look red. Okay, now let's do this one, y6 derivative. Okay, obviously we do it first with respect to x and then we do the substitution of x equal to 1. So we're gonna first do the derivative, but first we do the substitution from where? Right, so we do the substitution from there, from here. The derivative from the fifth derivative with respect to x, we're gonna do that one. Okay. So it's gonna be 4. The derivative of y primed is y double primed y primed plus 4y primed y double primed plus 4y primed y double primed. You keep 4y constant, you differentiate the double prime, it becomes a triple prime. Now this one is 2y primed plus 2. The derivative of the 2x becomes just 2. Okay, we just differentiating this, and therefore we're keeping things the 2. So this is going to be 1, and then the 2 here. So you have y primed and y double primed. And then here you have 2y. I mustn't lose concentration here. There's always a chance of mm, there's always a chance of forgetting where you were. And then now, okay, I'll have to just do it again from the beginning, just to because now sometimes I look at the too many times myself, wondering where I ended up differentiating. Okay, let's look at the 4y primed. So you have first the first y primed will going to be a double primed, keeping the second y primed constant, and then you have 4 y primed, and then the second y primed becomes y double primed. Okay, and then this one is 4y primed, so is 4y primed, y double primed, 4y, y triple primed. Then you have 2, which becomes 2, and then you bring down the 2, you have y prime, subtract 1 from the 2, which is the power, it becomes y primed just as it is. And then now you multiply by the derivative of the interior, y primed, it becomes a double prime. Okay. 2x, 2y primed, y double primed. The x is a derivative 1, y primed. And then y double primed. Plus, yes. Only x we've differentiated. Okay. Okay, I need to rectify something here small. Something small. It's the last one, this one. Okay, this thing can be done up to, it can be done indefinitely because it goes up to infinity. It's an infinite series of terms, but we speak about the truncated version of the Taylor series. So you're going to stop it at the sixth term. Right, because we understand now what's happening, so we don't need to keep, okay, where are we? Where are we? Where are we? Where are we? Okay, we're here again. We're here again. We're here. We just differentiated x there. Put the 3 ticks there. We just differentiate only x. So we must differentiate now. So we're gonna have 2x and then 2. Now we're gonna differentiate y primed. So it becomes double primed. And then we have y double primed. And then we have 2x, 2. Y primed is kept, everything else is kept constant. Y double primed becomes, is now differentiated, becomes triple primed. Okay, so we're done with this one. We're left with this one. Right, this is laborious a little bit, but it's too easy. Right, so next we have 2. Y. Y double prime becomes a triple primed. Okay, the derivative of the x is 1. You keep the triple prime constant, and then you have 2x. The derivative of the triple prime becomes the 4th prime. Okay. Okay, let me see now. Let's see what we have here. Okay, we continue, so we're done with that one. Okay, we're finishing. This is the last derivative, please. Right. This is the last derivative. Yeah, we're getting. Right. So, okay, I'm trying to also bring focus here. Okay, -6. We have this -6, the second derivative, y prime, y double primed, y double primed. So we're gonna differentiate the first one, becomes triple primed. -6, we double primed, and then we have triple primed. -6. Okay, so you have y first primed, you put double primed. -6 y primed, and then it becomes the triple primed becomes the 4th derivative. All right, we understand, I'm sure, the logic now, but it's just that, okay. Right, we have 2 y primed, y triple primed, so y primed becomes a double primed, and then we have the triple primed -2 y y triple primed becomes the fourth prime. So you have y primed, and then we have y to the fourth power. And then we have minus 2y. The y to the fourth power becomes the fifth power. Okay. The derivative of the last one, 6 is 0, because they're constant. Okay. Without wasting much time now, we proceed with the substitution here. Proceed with the substitution. So which means that we're going to do the sixth one, evaluate at 1. What is the second derivative? Is 2. The first derivative is also 2. The first derivative is 2. The second derivative is also 2. The first derivative is 2. The second derivative is 2. Y is 1. Okay. We get our substitution right and we don't repeat terms. So we try to be as pedantic as possible. Let me see. Okay. All these have 4 in front, but they're different. How many? 1, 2, 3, 4 of them. So there are 4 of these. 1, 2, 3, 4 of them. Okay, so we're dealing with the last 1, 2, 3, 4 of them. So this one is going to be the triple primed minus 4. We got it to be minus 4. Right, so we have 2 by 2. You can really as 2 by 2, you can write it as 4. Y primed is 2 and y double primed is also 2. We got that plus, excuse me. 2 into 2. Y primed is 2. Y double primed is also 2. 2. What is x? 1 into 2. Y double primed is what? Is 2. Another 2. X is 1, 2. Y primed is 2. What is y is minus 4? Minus 4 y triple primed. Plus 2. This is minus 4, the triple primed. 2 into the triple primed is minus 4. X is 1. The quadruple primed is what? Is 10. The triple primed is what? Is minus 4. The double primed is 2. Double primed 2, triple primed minus 4. Hey. Double primed 2, triple primed minus 4. Okay, you can always get this checked up. This one is 2. The primed. The quadruple primed 10. The quadruple primed 10. And then here the double primed 2. And then here the triple primed minus 4. Minus 2 into the white one is 1. And then now the quadruple primed, we found it to be 10. Okay, continue. Okay. Mhm. The third one. What is this? The third one. The second derivative. The fourth derivative is what? It's 10. White one is 1. Yes. And the fifth one, we got it to be 78. You see, the question we're then asking is, after all these, what is the result of this long calculation? Why the sixth derivative evaluated at 1, it's going to be the same as minus 152. Okay, you can cross-check that one. So, we're good. We're done? We're done with this one? Right, so we take all these values, substitute into this equation. So now, we proceed like this, as follows. Using the formula. Okay, there's a formula we wrote earlier. The formula was y evaluated at 1.1 is approximately y at 1, 0.1 at 1, 0.1, and then y double primed 0.1. Okay, we can put the factorials at the bottom. Y sixth derivative evaluated at 1. Even here you can put evaluated at 1. Right, so this is the result. But we substitute everything we got, so which means y.1, we can remember some of them. Okay, the things we don't remember. Like y1 we already know from the initial values is 1. And then y primed at 1, we know already is 2. Okay. Okay, look at this. So now, okay. Right, so yeah, I'm just checking the values that we're substituting the correct things here. But also, did we get y primed at 1? Yes. What was y primed at 1? Well, it's true, it was given in the question. And then we have 0.1. Okay, we're fine, we're good. I'm just cross-checking that we're on track. Yes, we're on track. Okay, look at this. This is 0.1. We square, we divide. And then now this y double prime, we got it. It was also 2, like y primed. Okay, this pattern continues, and then we have 0.1, we cube it. We divide by 3 factorial. And then what was the cube? It was minus 4. And then we have 0.1, we reduce to the fourth power. We divide by 4 factorial. Okay, what was the fourth one? 10. 10. And then 0.1 to the fifth. Oh, divide by 5 factorial. Then what was the fifth what? Derivative. Divided by what? It was 78. You can always cross-check these numbers. Right. We're just interested in understanding the methods here. So we have 0.1 to the sixth power. Right. So we have 6 factorial, and then the sixth one, we got it to be just about 100 minus 152. Okay, if we continue, so if we continue to do all these here, we're expecting the answer to be minus 1.2093 using calculator, 209381, 209381, 289. So using calculator, this becomes the result. So we have that. Okay, so this becomes the answer to the question. The couple of things, obviously, you can do here, and this does not mean that this can be solved only like this. But it is certainly one way to do this question. I'm going to give a comment here about other brief ways of solving this. So in other words, another student would approach this from the general formula point of view and say, any function can be written as a Taylor series like f evaluated at A, and then so you have 2 here. So plus. So you have 3. Okay. I gave this. I like this one because normally it looks like this at first here in terms of the functions and just not just y. But now in this module, obviously we do it like that. I want to just draw because you can find a general formula of these. First, you can find a general formula before you estimate. So because the question obviously said you need to solve this, so you can go up to n, the formula, the nth derivative, and then it is x minus a to the nth derivative, and then divide by n factorial. Okay, this is generally the Taylor series. If we speak about Taylor series, we mean this. Can we use it here in our context? This kind of Taylor series from first year. Or second year calculus, we do this. Maclaurin series is only when A is 0, is called Maclaurin. Right, so now Taylor is a more generous series than Maclaurin, obviously. But we are saying, for our purpose, what would y at x be? Which is the actual the actual solution. Okay, I'm going to write this one down because we've already done a lot of the derivatives, so we can use it to write these down. But I want to, okay, we're going to just remember the derivative. What was the derivative in the question? Okay, with that way, the differential equation we had to solve. So we were supposed to solve this one. We're supposed to solve d squared y, dx squared is x y squared 2y primed x cubed plus 4. Okay, this is the result. Rather the question. Y at 1 is 1, and then y primed initial values were given like this. Okay, okay, now we understand this. Okay, we understand this. Now, this was the question given. What do we do with this question? It was the question that we need to solve this differential equation and use the solution to this. So I'm saying then, what would the solution to the differential equation be? And I'm having a discussion before we move to the next thing. So the solution to this would be a function of x. So it could be y as a function of x equals. And then you have y. Okay, the red one is in terms of f. So what is A and what is everything here? Okay, so we were differentiating these things and we're finding f primed at 1. We're finding the derivative at 1. So in other words, it means that this one is y at 1, which is what we have obviously up there, this one. Right, so we continue. We have y uh, primed. So we would have all right. Okay, let me write like this. It's okay. Right, so I'm gonna write y primed at 1, and then we know what that is. We just substitute. All right, and then what is x minus a? So you can write it as x, which is the general solution as a function of x. So it would be this, but the a we can see is exactly what? The a is 1. All right, the a is 1. Okay, double primed. And then this one is 1. Okay, so I'm raising the most important point about the fact that we can solve the differential equation and find a solution without just estimating it at a given x value. In other words, given differential equation, you can find a corresponding Taylor series. Okay, and I must indicate that there's something called Laplace transforms that and Fourier transforms that work like these kinds, but the derivative is just an operator. Like the Laplace is an operator, linear operator, and the other one, the Fourier series, not in this module, of course, but yeah, in the third year. 370, 3701. Okay, because this is 3711. Okay, so now you have this one. Third derivative at 1, and then you have x minus 1. Okay, what have I done here? This one is 3. Yes, and then it's 3 factorial here. Okay, you can do look better. The fourth one, 1 x minus 1. This is 3. So this is 4. 4 factorial. Okay, this is 2. And then y fifth. Okay, I'm gonna stop at 6. Okay, this will just be actually the general solution to the differential equation, um, which is a Taylor series. Which is a Taylor series. Okay, last one. 6 6 factorial. Goodness me. Okay, this one. What is y at 1? Initial value 1 in the question. What is y double prime y primed at 1? Okay, initial value it is 2. Y double primed is also 2, we caught it. So the differential equation can be solved and we can find the actual solution to the differential equation as a Taylor series without what did we use to find these? We used the value, the initial values. Y at 1 and y prime. Okay, we're finishing this question, please. It is okay. What is y triple primed? Y triple primed is 4. X which is cubed. What is y fourth primed? We got it to be 10. Y fourth primed, we got it to be 10. 10 here. And then we have x minus 1. Y fifth prime. Okay, a bit it's 78. You can see it above in the blue color. Fifth primed. What about y sixth primed? We got it to be minus 152. Yes, y sixth primed. Well, the sixth derivative of y at 1. And then we have x minus 1, 6 over 6. Okay, this is the green one is the actual formula in terms of x. And then in it, we substitute 1.1. We substitute x equal to 1.1 because we need to estimate this at 1.1. And then if we substitute that, we're able to see the answer. And the answer is the blue one. Is the blue one. And that is the answer. Yes, please, my dear. All right, that's fine, my dear. Oh, okay, my dear. Okay, thanks, my dear. All right, we continue then. So now, this is the answer to the question. So just to recap quickly, as we move to the next one, we have to solve the differential equation given below by means of the Taylor series expansion. We have to solve the differential equation, which we did. Okay, I'm looking at the completeness of our response to get the value of y at that. Okay, so by means of Taylor series expansion, to get the value of y at 1.1, use the terms up to x to the 6th power and the change in x, which is 0.1. Okay, try to make sense of this because 99% of the times it's in the exam. So it's very important that you understand this. Okay, let's move on to the next question. Okay, the next one is the idea of what we call the simple Euler method. Right, the simple Euler method is a very important one. We have to spend time on the methods of Euler and the methods of Runge and Coulter. So, right, the simple Euler method is examinable normally if it's not Taylor or both is one of these, Taylor or the simple Euler method in the first question of the exam paper. So, first or second question, that is. Okay, now use a simple Euler method for the differential equation these with different values of h, 0.2 and 0.1 to get y at 1. Compare your numerical solution with the analytical solution of this. Okay, so we discuss the idea of the simple Euler, and then we shall look at other methods today. Right, let's discuss the simple Euler. It's a tabulation method. So we look at how we can tabulate things and be able to get the results we need. Okay. What is the formula for the simple Euler? What is the formula for the simple Euler? So it is y at 1 y subscript n plus 1 is equal to yn plus h f, it's xn yn. This is when they say simple Euler, use this one. This algorithm, call it formula algorithm. Right, so it is exactly yn plus h. Okay, it varies here 0 0.2, 0 0.1. Y primed at n. For simple Euler method, the simple Euler method, the algorithm is right. For simple Euler method, the algorithm is this one. Now let's use it to solve this. Use the simple Euler method for the differential equation with h. What are we using this Euler method for? We want to get y at 1. But we have been given that y at 0 is 1. But also the differential equation is this one. And with this notation, it is clear, and we need to know that y prime at n is actually what we call fn yn. So where we see fn yn is actually the derivative of y primed at n. Obviously, we can see here that y primed is x over y. So with this notation, we're able to see, therefore, that if we have y primed at n, it's fn yn. What is fn yn? Okay, if this thing here is that, so it's xn over yn. Okay, what is the meaning of all this? Obviously, we note that fxy is actually like that. What is the meaning of all this? We're going to construct a table for a is h is 0 0.2. Right, so we're going to do a, but h is 0 0.2. We're setting up putting our ducks in a row. Okay, I'm writing some of the formulas we have seen already from the previous page, but they're going to help us to construct the table of the solutions. Plus h y primed n. Fxy. And then this means y primed. Okay, we're just writing some of the notations we're going to use and what these things mean. For example, if we speak of f of xy, it means it is the derivative, which is x over y. All right, so we have everything here now. So we construct we arrange the calculations in the form of a table with columns. For x n, y n. Um, I prime. Now the table will be filled one row at a time. We use x n, y n to find the thing. So which means therefore that xn is what? Okay, h is 0.2. So if h is 0.2, so we start from what? Okay. The starting point is seen is evident from the given initial conditions and the differential equation at hand. So it's very important that I just note that one down. So we have that dy dx is a x over y for the simple oil. Well, this is just an example on the simple oil. And then y at 1 is 1. Okay. Okay, so we are saying y at 0 is 1. And we want to find, we are saying find y at 1. Okay, we're saying find y at 1. So in other words, but we understand that for the first one is that h is 0.2, which means is 0.0. Okay, and then now if we add 0.2, which is 0.2, we add another 0.2, 0.4, 0.6, 0.8, and then we add 0.2, you get 1.0. And then we have yn. Okay. What is y at 0? Is 1. So it's going to be 1.0. Okay. Now we're going to do the calculations. Let me just put the columns here. Then now we have yn primed. So okay, now let's complete this. What are the values in this table here? Let's see. I'll have to extend this a little bit. Hey, the table must be wide space. Okay, because some of the digits, all these numbers are a bit large. So obviously this is 1.0 yn evaluated at different values at 0 and so on. But I want to do this extend. So this one is yn primed, h yn. Okay, so we have this. So we can draw this one. After that, and then here we can draw this one. Just immediately after each variable, you draw a vertical line to construct the column. Let's start filling in the values. We're just practicing with this one. So we have the following. Need to be, we shall use our calculator. Right. What is y0? Y0. It is 1. So we shall put here 1. 0.0 to 1 decimal place for consistency. So what is the next one? Right, to get the next one, we use the formula. We use the formula yn plus 1, which is yn plus h x yn, which is yn plus h yn. So what is yn plus 1? Okay. Now here we got y0. Let's get y1, which is y0, h, x0, y0. Y0 plus h. F(x0), x0, y0. x0, y0. Okay, let's substitute here. What is y0? Okay, y0 is what we have at the beginning, and it is 1. H is 0.2 for this question. X0 is what? Is 0. And y0 is 1. And therefore this is only 1. So it means that now we are getting y1. Y1 is at one step. So h is 0.2, so this one is going to be 1.0 again. Right, let's find the next one, because it's not the same. Right, so we have y2. Let's find y2. Okay, we're using this formula. So y2 means that n is what here? means n is 1 in that formula. So which means is y1 plus h. We can use the other side. You can use the other one. My leader, long time, long time. You disappeared, my leader. Can we talk? Can I give you a call at 4? Is the task closing today? That's fine. Yeah, that's fine. Okay, because I'm in class now. As soon as I'm done with my class, I will give you a call so that we can do the task. Okay. Yes, I know, but yeah, but you have the question. Which assignment is it? Yeah, I have some of the assignments. I have. Yeah. Yes. Yeah. That's perfect to my leader. I'll just give you a call as soon as I'm done so that we can sort the task out. Okay. Yes. Thanks, my leader. Okay. Okay. Goodbye, my leader. Yes. Yes. Yeah, that one we're gonna sort it out because it's easy. My mechanics is not difficult. So yeah, we'll sort it out. Okay. Yeah, that's fine. Even if you're writing today, we're gonna make a plan today. Yeah. So yeah, it's okay, my leader. I'll give you a call as soon as I'm done. Okay. Okay. Thanks, my leader. Goodbye, my leader. Goodbye, my leader. Great. Right. My apologies for really having to speak to this student. He did not even tell me he was going to call me. Okay, but I know that sometimes it becomes too desperate. Okay, if you have y2, for example, it's going to be this y1. So what is y1? Is 1. H is 0.2 in the question. X1 is what? So X1 now is going to be 0.2. The first X at the first step. Because the step or the H is 0.2. Sort of a step size, we are moving in steps of X. Right, migrating away from the origin when X increases. Okay, you're going to see what that means. What is Y1 is 1.0, but just 1. Okay, what is the answer to this? Okay, we can just do this quickly. So it is 1 plus that. So what is 1 plus that? Right, so 1 plus that is going to become 1 plus 0.2 times 0.2. Yes, it's correct. 1 comma 0.4. So which means this one is 1 comma 0.4. Okay. It corresponds with the one in the material I'm using. So I always have references. Normally, we practice existing questions just to make sure you understand the methods. Right, so we have this. Right, so but I will have to do this now. But this table is going to be confusing very soon. It's going to be a total mixture of things. Right, just to draw some horizontal lines here. Right, just some horizontal lines so that um okay. Let's just complete it. So we're going to complete it in blue and complete it quite quickly and see what we get. Okay, for example, now what is y3 here? And then we're going to do y4, we're going to do y5. And then we're going to do the primes and the h prime. So this, and we're going to analyze what this means in view of the question at hand. Now, if you have this, let's do the next one. So I'm going to use the eraser super fast. This eraser, now we're going to do y3, so just change these subscripts here. And then change this. Okay, then change this. So now let's see what you can do. Now, this one here, okay, so we're doing y3. So if it's 3 here, it means n is 2. N is 2 in this one, n there. So if n is 2, then this one is going to be 2. 2, 2. What is y2? 1.04. 0.2. What is x2? X2 is the next one. X1 is 0.2, but the x2 is the next step, which is 0.4. And then y2, we got y2. We got it to be 1.04. And then what is the answer to this? Okay, we use a calculator for this. Use the calculator here, which is 1.04 plus 0.2 plus 0.2. This one you can even do it using our calculator here. Let's see what we can do. Just 1 sec. Right. Right, so I wanted to bring something else. Just 1 second. I want to bring a calculator you can use so that maybe it can be practical for you to see what is happening here. Normal. Okay, just forgive me for putting this down. I need to get activate my calculator here. Where's the calculator? Where is it? I don't like closing my screen. Okay. I'm at this calculator now. I can put it at the bottom like this. And then I can get back here. Okay, the calculator is already there. You know, if I do this, right, and this be done, it will disappear. Okay, that's fine. Okay, let's use the calculator now. Right, if we use this calculator, what did we get? Right, so, right, that's fine, I've put it down. So you see that we have 1.04 plus 0.2 plus 0.4 divided by 1.04. Right, so yeah, I'm gonna be quick, please, because this is just one more thing. So I'm gonna punch it on the calculator. You know, I can have a better way to do it here. Right, so 1.04 should not take long. Hey, you see the blue one? Just gonna experiment this 1.04, 0.2, and then you have 0.4, and then you have 1.04, and then we're gonna get the results, and then we're gonna plug it into the table. But yeah, okay. Suppose you have this into we have 1.04 plus 0.2 by 0.4 divided by 1.04. Okay, see what we get. Okay, this is giving exactly 1.116. Let me check in my records. It is the correct answer. So effectively what this means is that what you're having here, and write it here. So the y3 now is 1 point. Right, you can take it, we can take it back. Right, the y3 now is actually 1 point. Right, so the y3 now is 1 point. Is the word sick? Right, so we have that. Right, so that's fine. Well, this needs to go back to the actual mode, actual presentation mode. Right, so that's fine. Let's see. Okay, it's the same thing. Right, I'm going to enlarge it just now. But if you okay, it's okay. I can take it back to this. Right, so what you're getting here, this one, I got it. Okay, but it now is 1.1169 23077. Okay, if we continue, we'll get y4 1.22 43 61 094 y5. Okay, we continue in the same way. Okay, so we have seen already the method. So it's exactly what we get here, 1.355. Right. So see now, yeah, this can make better here. 0.4. 1.4. 9.6. Okay, you can see in the way we did the y3, then you can do the rest of these. What about the y primed now? Let's see the y primed. Okay, the y primed can be done in a similar manner using the y primed formula. What is the y primed formula? Okay, in this method, we can see that this one is used for what? To get the successive y values from the initial one that's given in the initial value problem. But the y primed has its own formula. It is exactly the yn primed. And the yn primed is the differential equation. Here we just divide x and y. So which means that we put x on top and y at the bottom. So which means x, we're going to put 0 0.0, 1.0, 0. Okay, to 1 decimal place. X first, 0 0.2, you divide by 1.0. What is the answer? It's 0 0.2 because 1.0 we're dividing by just 1. And then now you have x, which is 0 0.4. We divide 0 0.4 by y, which is 1.04. And then, okay, this one needs another calculator. Let's see if this calculator can be of assistance here. So we have, let's just practice. So I was saying 0 0.4 0.4 you divide by 1.04. And then what is the result? 0.38. That's the correct answer. So you have 0.3846. I have it here. 3846, 15384. Okay, you divide again 0.6 divided by y. 1.11. This is a simple Euler. You just learn the table and you can complete the table the whole time. 3027. Okay, just practicing, and then the other one we're gonna just write it because I've already done it here. So, which means now we're gonna say 0.6 you divide by 1.1169230. 77. 3077. Okay, so this is about 0.53. Um, 7 and so on. Okay, if we continue, here we get 1.2. Just divide x by y. We get 1.22. 43. 61. 0.94. Dividing x by y, x divided by y, we get 1.35. 5041496. Okay, that's simple Euler. And then the next thing is we just multiply. So we multiply h. H we know is already 0.2, but we multiply by the y primed, which comes from here. So like here, we're going to say 0.2 times the 0.0, which is 0.0. And then here we have h is 0.2 for this question, and then multiply by y, which is 1.0. 1.0 is just 1, so it's 0.2, this one. And then you multiply 0.2 by the y primed. 0.3846. And then if you multiply everything, 0.076923076. 0.53. 1.0. If you multiply this one, 1.074. 38016. Okay, here you take 0.2, you multiply by the y primed. 0.1074. 38016. 0.1074. 38016. So you have this one is 1.355, which is 0.30680402. So this is the method we're using. But now, okay, I want us to say something about this solution. I want us to say something about this solution. Uh-huh. All right. So, let's say more. The next slide. Right, on the next slide, we're going to comment about the analytical solution. The analytical solution is, which is y squared right, the analytical solution is y squared is equal to, okay, 1 plus x squared. How? Okay, you need to first remember right, that dy dx is so, which means, okay, this one is separable. We can solve it. It's a separable differential equation from first year calculus. We can be able to solve this just a simple cross multiplication yields this. We apply the integral sign. This integral sign is the symbol S for summation. And then we have half y squared, half x squared plus a constant, but we have the initial value y at 0 is 1. For us to find the value of the constant c, goodness me, c is 1/2. So c is 1/2, you multiply through by and divide through by the 1/2. That is how the analytical solution is that. Now, what is the use of this analytical solution? Why are we even getting to it? Because they said here, compare your numerical solution with the analytical solution. By good luck, they gave that, but we can find it from the differential equation anyway by using methods of solving differential equations. Okay, we can make y the subject is easier here. Y is plus or minus the square root of x squared plus 1. All right. So y is plus or minus the square root of this. The plus sign gives a solution to the initial value problem. This is normally called an initial value problem, IVP. And this happens with y0 equals 1. That is the initial value. At x equal to 1, we take the positive, the plus sign. So you have plus, which is 1 plus 1 squared. Okay, so we're going to draw a table. And then you have the exact solution. Right, so we can see the exact solution is the square root of 2, but the square root of 2 is evaluated at 1. What is the exact solution? Because we want to give an estimate. We're asking the question, what is y at 1? We know that y at 0 is 1. We're using Euler to find y at 1. But the exact solution to this is y at is the square root of 2. But the square root of 2 is what? Is 1 point something? 1.41421213562. Okay. What now we're gonna draw this table now for the final answer. So we find the exact solution, which is 1.414213562. That is the exact solution. The error, okay? So here we're gonna have Euler. Here Euler was used with h equals 0.2. H at 0.2, what did we get it to be? We got it to be 1.3107. Wait a minute. 96. It is this one. 1.35504196. 1.355. 1.3. 1.3. 55041 041496. The error. Right. So now let's just compute the difference between the exact and the estimate. Hey, so let's just do that one. The calculator is going to pop in, but it's going to sit. Fine. Go sit on the stuff. All right. Now we can move it normally. Right. So let's just find a difference here. So we have the exact, which is 1.41443,562. Okay, long digits here, 1.355041496. So we can get the error, which is 0.05 that. 66. Okay, if you subtract these, exact minus the estimate is 0.059, so we can find the error. The difference between the exact and the what? And the one obtained using Euler with h equals 0.2. Okay, but also so there are two values. By using Euler, we're able to see that y at 1 is approximately, okay, in the question, we know that y at 0 is 1. Okay, the initial what? Initial value. But here we know that with Euler, we got it from the table. This one here, it is clear that y at 1 is approximately 1.3. Is approximately 1.3 by 504 1496. Okay, it is y at 1. So at 1, we have this one. We have this one, which is exactly the estimate. Okay, which is what the question wanted. But also, in other words, the question said you need to use the simple Euler method for the differential equation given with h equals 0. We did 0.2, but 0.1 can be done the same way. You get y at 1. What is y at 1? And then after you got y at 1, compare your numerical solution with the analytical solution which is the analytical solution of the exact. So now we have got the solution for using Euler method, using the simple Euler, using the simple Euler method. What is the solution? It is the y value. What is the y value? Right, it's the y value there we got. Okay, it's fine. Is this one? Which is this one? White one is that one using Euler. With the analytical, we can use this one was clearly separable differential equation. They just gave us a solution to it just in case. Obviously, don't need to waste time solving that. It's a first year thing. And then now we get the exact one. The exact one at 1. White one exact is the square root of 2, approximately 1.41. That calculator. used. And then here the Euler is this one. And then the error, the difference between the exact and the exact solution and the Euler, the one obtained by Euler, is that one. Okay. I think that in view of our time is about 3. Let me see now. I'm looking at the bottom of the screen here. It's 3:33 p.m. We started at approximately 1:02 p.m. Thereabout. Okay, this is fair enough. We shall meet again on Thursday. Right. So on Thursday, we shall meet again at 1 p.m. and then we shall continue to look at other methods and understand this module better. Yeah, there are a lot of methods which we're going to look at that are examinable, like your Runge-Kutta and other methods that are examinable. Yeah, but I must thank you for joining us today and see you again on Thursday at 1 p.m. Okay.
Is it this Thursday?
Yes, this Thursday. Right. Do you think about it? Let me know if it's ideal for you.
Okay.
Yeah, I'll try to get more interesting questions that you can discuss on the examinable topics. So I just practice the topics and the methods that are to be learned for the exam, because these are the kinds of methods you just need to sort of understand. If they say simple Euler, you've seen simple Euler. If they say the Adams-Moulton, you've seen that, but you might need to just reinforce. And also I prepared today a couple of other things, but shall not quite get to it. You need to take a break. Okay, this we looked at, but the couple of other methods I wanted us to discuss in view of this. Okay, we looked at these already, but a couple of other things we actually had to discuss here. Okay, we did the per day and so on, but I wanted us to look at a bit more general consolidation question on these things of the share by share of polynomials. The it goes with the per day approximation method. Like here, when they say find a per day approximation R6. Okay, R6, obviously we understand that this has to do with the degrees, the degree of the rational function. We discussed it. So I planned an example, this one, to sort of consolidate that. And then I planned that if time would allow, would also go to look at just the idea of finite differences, because it's very important. The method of finite differences hinges on the ADI method, which we looked at last time, and the SOR. Right. So now those two methods, they hinge on what we call the method of finite differences. And we looked at the grid that is used and the table that is drawn with sort of grid points on it. Right, in view of the assignment, we discussed briefly, but yeah, those are the kinds of things I planned. But I know very well that we shall have a discussion to sort of reinforce this. I'm planning that on Thursday we try at 1 p.m. to do get other things. Your method of finite differences, your Runge-Kutta is very important that we spend time on Runge-Kutta of up to fourth order. Second order, third order, up to fourth order. Okay, I'll give reasons why that, because that's what is examinable. All right. Yeah, this coming Thursday is what I'm planning. But thanks a lot for this discussion. I'll see you again on this Thursday, 1 p.m. Okay. Okay, goodbye. I'm gonna upload the video in the next couple of minutes.